Welcome to the deep dive. We cut through the noise to get you the essentials. Today, we're tackling something really foundational. It helps us make sense of uncertainty everywhere. Think weather forecasts or, stock market moves. We are diving deep into probability distributions. Now, these aren't just math concepts. They're basically the language we use to understand randomness. And crucially, to make predictions in data science and, well, tons of other areas.
Exactly. Yeah, and our mission here is really to unpack the most important ideas, the key distributions that data scientists actually use. We want to cut through the complexity, give you a really clear picture of what they are, why they're so important, and how they get used in practice. Think of it as getting a handle on the surprising order you can find in, well, what looks like chaos.
Right. And to help us navigate this, we've looked at a bunch of sources. Articles like 4 probability distributions every data scientist needs to know. From Built-In, another good one, 6 types of probability distribution in data science. From Analytics Vidya, plus some solid study guides on probability itself.
Okay, so to really get this, we should probably start with the absolute basics. Probability theory 101, almost. Like, what's an experiment in this world? It's just a repeatable process, right? With known outcomes.
Yeah, exactly. Like rolling a standard die. That's your experiment. And the sample space is just all the possible things that could happen. For the die, that's 1, 2, 3, 4, 5, 6. Simple as that. And an event, that's just a single go at the experiment. One roll of the die.
And there's this interesting split, isn't there, between theoretical probability,
Right.
which is what you calculate, like 16 chance for rolling a 3.
Based on the possibilities, yeah.
And then experimental probability,
Yeah.
which is what you actually get when you start rolling the die many times. And the cool thing is, if you do it enough times, lots and lots of trials, that experimental result gets closer and closer to the theoretical one. Like, roll it 100 times, you might get something near 16 for each number. Roll it 1,000 times, it'll almost certainly be even closer to that 0.166. It sort of converges.
Okay, that makes sense. So from experiments, we get random variables, RVs. These are just variables where the value comes from the outcome of that random experiment, right?
Precisely. So X could be the number you roll on the die. Its value depends on chance. And these RVs, they come in 2 main types. You've got discrete ones.
Discrete, meaning countable.
Yeah, countable, distinct values, like the numbers on the die, 1 through 6. Or, say, the number of items someone buys online. You can count them. Then you have continuous random variables. These can take on basically infinite values within some range.
Like temperature or height.
Exactly. You measure them, you don't count them.
Yeah.
There's always a value between any 2 other values.
Got it. So we have these random variables. How do probability distributions fit in?
Well, a distribution is essentially just. It's a way to organize and show all the possible values a random variable can take, along with how likely each value is. Often you see them as graphs, right? It gives you a picture of the data's shape. Helps you understand the underlying pattern.
So when you see a data set, you're looking at a sample, and the distribution helps you infer about the whole population.
Pretty much, yeah. And we use 3 main stats to describe these distributions. First, the mean. Everyone knows that one. It's just the average. Add them up, divide by how many? Like for 4, 7, 6, 3, 1, the mean is 4.2.
Okay, standard average.
Then variance. Sounds a bit technical, but it just measures spread. How far, on average, are the data points from that mean? You calculate the difference for each point, square it, then average those squares. For that same set, 4, 7, 6, 3, 1, the variance is 5.7. Tells you there's a bit of spread.
Right, so it quantifies the dispersion.
And finally, standard deviation, which is simply the square root of the variance. It gets you back to the original unit, so it's often easier to interpret. It's just another way to measure that spread.
Okay, this is where it gets kind of cool, especially for data work. These measures, mean, variance, they behave in predictable ways when you mess with the data, right?
Oh, absolutely. Key properties. Like if you add a constant value to everything, say, everyone gets a $10 K raise.
The mean goes up by $10.
Right, obviously. But the variance, it stays exactly the same. Because everyone moved together, the spread didn't change.
Ah, interesting.
But if you scale the data, like multiply all salaries by 1.5.
Then the mean scales by 1.5 too.
Yep. But the variance scales by the square of that factor, so 1.5 squared. Because the distances stretch out more. Understanding this is critical for things like data normalization.
Okay, that's a really important distinction.
And to actually define the probabilities, we use specific functions. For discrete variables, like our die roll, we use the probability mass function, or PMF. It gives you the probability of getting exactly a certain value. The probability of rolling a 3 is 16. The PMF tells you that mass.
Okay, mass for exact values.
But for continuous stuff, like height, The chance of being exactly 5'10" is basically zero. It's too precise.
Right.
So we use the probability density function, or PDF. It shows the density of probability around values. The area under the PDF curve between, say, 5'9" and 5'11", that gives you the probability of being in that range.
So density, not exact probability. Got it. And you mentioned CDF too.
Right, the cumulative distribution function.
Mm-hmm.
It works for both discrete and continuous. For any value x, the CDF tells you the total probability that the random variable is less than or equal to x. It accumulates the probability.
That sets a really solid foundation. We have the variables, ways to describe their spread, and functions to map their probabilities. So now, the distributions themselves, you hear about loads of them, but data scientists seem to focus on a core few.
That's right. While there are, dozens, maybe hundreds of distributions out there, most of the time, data scientists rely heavily on about 6 main ones. These are the real workhorses.
Okay, let's dive into them. What's the first star?
First up has to be the normal distribution, also called the Gaussian distribution.
The bell curve.
The bell curve, exactly. It's famous for that symmetric shape. And it pops up everywhere in the real world. People's heights, errors in measurements, blood pressure, test scores, loads of natural phenomena tend to follow it.
Why is it so common?
Often is because the thing being measured is the result of many small independent random factors all added together. That tends to produce a normal distribution. And you have the crucial 68, 95, 99.7 rule.
Ah, yes. Tell us about that.
It means about 68% of the data falls within one standard deviation of the mean, 95% within two, and almost everything, 99.7%, within 3 standard deviations. Super useful rule of thumb. It's also vital for certain machine learning models, like Gaussian naive Bayes. And sometimes, if your data isn't normal, you can transform it to make it more normal, which can really help your analysis.
Okay, normal distribution, the big one. What's next?
Next, the simplest one, the Bernoulli distribution.
Bernoulli. Sounds familiar.
It represents just a single trial with only 2 possible outcomes. Success or failure, heads or tails, click or no click, buy or not buy. That's it.
So like one coin flip.
Exactly. It's the absolute basic building block. The probability of success is p, probability of failure is 1p. The mean is just p, and the variance is p times 1p. Dead simple, but foundational.
Okay, number 3.
Number 3 is the uniform distribution.
Uniform. Just everything's equal.
Pretty much. Within a specific range, every outcome has the exact same probability. Right. If you plot it, it looks like a rectangle, flat top.
Examples.
A fair coin flip is uniform. Heads, 0.5. Tails, 0.5. Rolling a fair die is uniform. Each face 16. Generating random numbers in a computer simulation often uses a uniform distribution as a starting point. Or say, a flower shop's daily sales are uniformly distributed between 10 and 40 flowers. The chance of selling between, say, 15 and 30 flowers on any given day, you can calculate that easily from the range. It'd be 30-15, 40-10, which is 15-30 or 0.5.
Okay, equal chance within a range. Makes sense. What's number 4?
Number 4 builds directly on Bernoulli. It's the binomial distribution.
Binomial, so multiple Bernoullis.
Exactly right. It describes the number of successes you get in a fixed number of independent Bernoulli trials.
Okay, so not just one coin flip, but maybe 10 coin flips.
Perfect example. How many heads do you expect in 10 flips? Or if a marketing campaign has a 10% success rate, P 0.1, and you send it to 100 people and 100, how many people are likely to respond? That's a binomial question. Key things. Fix a number of trials, only 2 outcomes per trial. Trials are independent, and the probability of success stays the same for each trial.
Got it. Connects directly back to Bernoulli. Halfway there. Number 5.
Number 5 is the Poisson distribution, named after Simeon Denis Poisson.
Poisson. That rings a bell. Call centers, accidents.
Yep, exactly that kind of stuff. It models a number of events happening in a fixed interval of time or space, like the number of calls arriving at a call center per hour, or number of emails you get per day, or car accidents on a certain road per week, or even like the number of typos on a page of text.
How do businesses use this one?
Oh, heavily. For forecasting demand, like how many customers might arrive at a store in the next hour, helps with staffing. Or predicting sales to manage inventory. Very practical. It assumes events happen independently, and the rate is constant over the interval.
Okay, counts of events in an interval. And the last one, number 6.
Last of the big 6 is the exponential distribution.
Exponential growth. Decay.
Sort of related, but here it's about time. Specifically, it's a continuous distribution that models the time between events in a Poisson process.
Ah, so if Poisson counts the events in an interval, exponential measures the time until the next event.
Exactly. Like how long do you have to wait for the next customer to arrive? Or how long until a machine part fails? A really unique thing about exponential is its memoryless property.
Memoryless. What does that mean?
It means the probability of an event happening in the future doesn't depend on how much time has already passed. So if a light bulb has an exponential lifetime distribution and it's already been working for 100 hours, the chance it lasts another 50 hours is the same as a brand new bulb lasting 50 hours.
That's counterintuitive.
It is, but it's a key property. It makes sense for things where failure is random and not due to wear and tear, like radioactive decay or maybe some types of electronic component failures. It's used a lot in reliability engineering and survival analysis.
Wow. Okay. So those are the 6 big ones. Normal, Bernoulli, uniform, binomial, Poisson, and exponential. Quite a toolkit. But you mentioned they're connected, right? It's not just 6 separate tools. How do they relate?
Yeah, absolutely. There's a real elegance to how they fit together. Some are even special cases or limits of others.
Like how?
Well, we already said Bernoulli is just a binomial distribution with only one trial, N1. And Poisson can actually be seen as a limiting case of the binomial. If you have a huge number of trials, N is very large, but a tiny probability of success on each trial, P is very small, such that their product NP, the average rate, is moderate, then the binomial starts to look very much like a Poisson.
Interesting. So lots of opportunities for a rare event.
Exactly. Also, the normal distribution can approximate the binomial when N is large and P isn't too close to 0 or 1. And the normal can also approximate the Poisson distribution when the average rate, lambda, is large.
So the normal curve pops up as a limit in several places.
It does, which is partly why it's so central. And remember, the exponential distribution describes the time between events in a Poisson process. They're intrinsically linked.
Understanding these connections must give data scientists flexibility, right? To choose the best fit or maybe approximate one with another sometimes.
Definitely. It helps you see the bigger picture and choose the right tool or know when an approximation is valid.
Okay, so we've got the distributions. Let's go a bit deeper. What do they tell us about the shape of our data beyond just the average or spread? You mentioned asymmetry earlier.
Right, skewness. That's a really important concept. It measures how lopsided a distribution is. Does it lean to one side, or is it nice and symmetrical like the normal distribution?
And you can spot this visually, usually.
Often, yes. When you plot the data, a histogram say, you can frequently see if it's skewed. It's a key thing to look for because many statistical techniques work best with symmetrical, non-skewed data. We basically talk about 3 types. Zero skew is perfectly symmetric, like the normal distribution. Mean, median, and mode are all the same, right in the middle.
Okay, balanced.
Then positive skew, or right skewed. This means the tail stretches out to the right. Most of the data is piled up on the left side. Think about income distribution. Most people earn a moderate amount, but a few earn very high amounts, pulling the tail out to the right.
And in that case, the mean gets pulled higher than the median.
Exactly. The mean is pulled right by the high value, so mean, median, mode typically.
And the opposite.
Negative skew, or left skewed. The tail stretches out to the left. Most data is clustered on the right. An example might be grades on an easy test. Most students do well, scores clustered on the right, but a few might do poorly, pulling the tail left. Here, mean, median mode.
So why is identifying skewness so critical in practice? Does it break things?
It can, yeah. Many linear models, for example, assume variables are similarly distributed. If you have a highly skewed predictor variable, it might affect the model's performance. Think about predicting car MPG using horsepower. Horsepower is often right skewed. The relationship might be different for low HP cars versus high HP cars. Skewness also tells you where your outliers are likely to be in the direction of the tail. And highly skewed data can sometimes give misleading results from certain statistical tests.
But you're not stuck with it, right? You mentioned transformations.
Correct. If you have skewed data, you can often apply mathematical transformations like taking the logarithm or a square root or something called a box-Cox or power transformation to make the distribution more symmetric.
And that helps the models work better.
Often, yes. It can stabilize the variance and make patterns clearer, leading to better model performance and more reliable results. It's a common step in data preprocessing.
Okay, that's super useful. Now, let's shift gears to another really big idea. You hear it called the unofficial sovereign of probability theory, the central limit theorem, CLT.
Ah, yes, the CLT. It's pretty fundamental, maybe even a bit magical, like you said earlier.
So what's the core idea? Why is it so central?
The core idea is quite profound. It states that if you take a sufficiently large sample size from any population, doesn't matter what the original population's distribution looks like, could be skewed, uniform, anything that the distribution of the sample means will tend towards a normal distribution.
Wait, the distribution of the means, not the original data.
Exactly. That's the key. You take lots of samples, calculate the mean for each sample, and then plot the distribution of those means. As your sample size gets bigger, that distribution of means will look more and more like a bell curve.
Regardless of the original shape.
Regardless, as long as the original population has a finite variance and the samples are independent and identically distributed, it's incredibly powerful. Think about rolling dice again. One die is uniform. But if you roll, say, 10 dice and calculate their average, then do that whole process thousands of times, the distribution of those averages will look remarkably normal.
That's amazing. And it has a long history, doesn't it? Not just one person figured this out overnight.
Oh, absolutely. It evolved over centuries. De Moivre had an early version way back in 1733, mainly for binomial cases, but it wasn't widely recognized. Then Laplace expanded on it significantly around 1812, but again, it didn't immediately catch on.
So it took a while to appreciate its importance.
It did. Alexander Lyapunov gave a more rigorous proof around 1901, and the actual name central limit theorem was coined by George Polya in 1920 because he felt it was, well, centrally important to probability. Even Alan Turing worked on a related proof.
Wow. So given its importance in history, are there still things people get wrong about the CLT misconception?
Surprisingly, yes, even in some textbooks. A big one is forgetting it applies to the distribution of sample means, or sums. Not just randomly sampling individual values. Taking lots of individual values won't magically make that sample normally distributed if the underlying population isn't.
Okay, it's about the means specifically.
Right. Another huge one is the rule of thumb about sample size. You often hear 30 is enough for the CLT to kick in.
Yeah, I've definitely heard that.
It's not really based on solid theory. It's a bit of a myth. How quickly the distribution of means becomes normal. Normal really depends on how skewed the original population is. If the original data is heavily skewed, you might need a much larger sample size than 30 for the normal approximation to be any good. There's no single magic number.
That's crucial to know. So how does CLT relate to the law of large numbers? They sound related.
They are related. Both deal with what happens as sample sizes get large. The law of large numbers basically says that the sample mean will get closer and closer to the true population mean as a mean increases. It tells you where the center converges. The central limit theorem gives you more detail. It tells you how it converges specifically. It describes the shape of the distribution of those sample means around the true population mean, saying it becomes normal. It gives us the shape, which is vital for inference.
Which leads us nicely into statistical inference, using samples to say something about the whole population.
Precisely. Statistical inference is all about that, drawing conclusions, making estimates, testing hypotheses about a population based only on sample data. It's the foundation of, well, most data analysis and machine learning.
How do distributions play into inference?
They're essential. We use them to model the uncertainty in our estimates. Techniques like maximum likelihood estimation, MLE, try to find the population parameters like the mean or standard deviation of a distribution that make our observed sample data most probable. Or there's Bayesian inference, which is really powerful. It combines prior beliefs or knowledge about parameters, maybe expressed as a probability distribution, with the likelihood from the observed data to get an updated understanding, again, often in the form of a probability distribution. Great for complex problems or when you have limited data.
So inference lets us quantify uncertainty. What about when things are just too complex to model directly? I've heard about Monte Carlo simulations.
Ah, Monte Carlo. Yes, a fantastic technique, especially when dealing with lots of interacting uncertainties or risks, named after the casino, of course.
Because it relies on randomness.
Exactly. The basic idea is, if a system is too complex for exact math, simulate it many, many times using random inputs based on probability distributions.
So you define your uncertain variables.
Right. You figure out which parts of your model are uncertain, maybe future interest rates or material strength or project task durations.
Then you assign probability distributions to them, like interest rates might follow a normal distribution, task times maybe an exponential.
Exactly. You pick the distributions that best represent the uncertainty for each variable. Then the computer generates thousands, maybe millions, of random scenarios by sampling values from these distributions. It runs the model for each random scenario. And by looking at the range and distribution of the outputs across all those simulations,
you get a probabilistic forecast, like the probability of finishing the project on time or the range of likely investment returns.
Precisely. It lets you quantify risk and understand the range of possibilities in a way that simple deterministic models just can't. Incredibly useful in finance, engineering, project management, loads of fields.
Okay, this has been a fantastic tour through the world of probability distributions. Pulling it all together for our listener, why does all this matter? Beyond the data science lab, where does this impact you?
Oh, it impacts you constantly, often invisibly. Weather forecasts. They use probabilistic models based on distributions. Stock market analysis, full of attempts to model the distribution of returns and risks. Machine learning algorithms powering recommendations or translations. Many rely heavily on probabilistic foundations.
And in other industries.
Everywhere. Finance, as we said, for risk. Portfolios, predicting defaults. Engineering, predicting when bridges might need maintenance, or how reliable a system is based on component failure distributions. Supply chains, forecasting demand, managing inventory levels using things like Poisson or normal distributions.
Project management.
Yeah, figuring out the probability of hitting deadlines, healthcare analyzing clinical trial results, modeling how diseases spread, understanding drug efficacy, even how neurons fire, quality control in manufacturing, using binomial to check defect rates. It's truly embedded in the modern world.
So fundamentally, it's about making better decisions when faced with uncertainty.
That's the core of it. Understanding these concepts lets you look at data or a situation and not just see the surface, but understand the underlying probabilities, the range of outcomes, the potential risks and rewards. It helps you find that order within the noise, especially when things aren't obvious.
What a journey. We started with basic probability, met the big six distributions, normal, Bernoulli, uniform, binomial, Poisson, exponential, saw how they connect, and then explored skewness and the powerhouse central limit theorem, plus inference in Monte Carlo. It's really clear these aren't just abstract math ideas. They are absolutely critical tools for anyone trying to understand and navigate our complex, data-filled world, finding those patterns in the chaos.
Absolutely. And maybe a final thought to leave you with. Sir Francis Galton, who was fascinated by the normal distribution in CLT, marveled at how this law of frequency of error, as he sometimes called it, could bring order out of apparent chaos. He wrote about observing the wildest confusion, yet finding it reduced to the most beautiful form of regularity. So maybe consider, as you go about your day seeing things that seem random or chaotic, how might understanding these underlying distributions, these hidden patterns of probability, change how you perceive that randomness? Where might you find surprising regularity amidst the confusion?